Hi, welcome to Lecture 10 in this series for an Introduction to Proof course. Today we're going to go through some basic elements about logical equivalences, how to understand when statements are logically equivalent, and then how to actually argue that they are, in the case that they are. So we'll start off with some basic notation and a few key ideas. Then we'll talk mostly about proving equivalences. The middle part here is the meat of it. Provided there's enough time, I'm going to also mention one of the things that's in the exercises in a general introduction to math. And there's a bunch of exercises that are about the island of knights and knaves, a mythical place where, well, let's get to that if we get to it at the end. So getting started, the in the last section we actually saw that a conditional and its contrapositive are the same. The big question is, what precisely did I mean by that? Um, there's multiple ways to go about this, but a good, what's known as an operational definition, a way that you can distinguish, is this: make a truth table. Use the same pattern of trues and falses in the columns that correspond to your input variables, and then make a truth table for each of these statements. If you see an exact correspondence, literally right down the rows of the truth table for both of them, then they're equivalent. That's what we mean by a same. Oh, I just used the word right before I hit the punchline moment here. So yeah, we call that logical equivalence when in a truth table the two things have identical truth values right on down the line. There are two notations that are in use for this. One is the double-headed arrow, which we've seen before in definitions. So but when we say, the name of some concept, like, x is an even number, and then the defining property for that concept are the same, we're using the same notion here. They're logically equivalent. The other notation, which I actually prefer, is a sort of an equal sign with a little squiggly decoration on top. The thing to take away from this is you don't want to be writing something like A implies B is equal to not B implies not A. Why? Because, well, the equal sign is already for something else, right? You put equals in between two numerical values that are equal. We actually already overload that operation quite a lot. We, for instance, use equals as written there, an unadorned equal sign in between two sets that have exactly the same entries in them, which arguably is a bad thing to do too. But in logic, there's another symbol available that makes perfect sense. So we shouldn't just reuse the equal sign here. So what can you do? You can either write, well, you see what we're seeing there, the two conditionals, the original A implies B and its contrapositive on the right, and in between, and we put parentheses around them because it's not clear what the precedence of operators is between the double-headed and the regular arrows. Some people say the regular implication has higher precedence, so we wouldn't need the parens. Other people say these are all at the same level. It never hurts to put in extra parentheses. So this is saying A implies B is true exactly when its contrapositive statement, not B implies not A, is true. This is probably the more popular notation, to use the double-headed arrow, the if and only if symbol. So I'm not just trying to be a contrarian here. I really do prefer the funny version of the equal sign. Did I say why in here? Well, let me speak for a second about why. When I see this line here, I feel that I'm looking at a single logical expression, and that's true. In fact, I am. What we're saying is we're sort of asserting the truth that these two left side and right side things can be stuck together with the biconditional. We're asserting that to be true. But on the other hand, when I see this expression, at least to my eyes, this looks like more a comparison of two things rather than one thing. That is, we've got a thing that's on the left of the funny equal sign, we've got a thing on the right of the funny equal sign, and it's saying that left and right sides are equal. So this one, this version of things, at least for me, feels more like it's showing the idea of a balancing between two things, that they balance, that they are the same. That's probably just personal prejudice. It may even be the fact that I believe that's the notation they used when I first learned the topic. So I'm sort of stuck in an old school thing. But yeah, anyway, we'll stick with it. But you should be ready to switch at a moment's notice. It's really not that big of a deal, right? The funny equal sign and the double-headed arrow literally are synonyms. They're two different ways of saying the exact same thing. Well, it turns out that lots of compound sentences are equivalent. So, again, repeating what that means, in every possible scenario, and the rows of a truth table should be thought of as possible scenarios. Those are places, each row indicates a different pattern of true and false on the input variables, the predicate variables we're using. So if in every possible scenario they give you the same result, that's a pretty strong sense of equivalence. Here's a great example. A or B is exactly the same meaning as A or not A and B. Feels like it couldn't be, right? You've got more stuff there. There's an or and an and. On the left, it's just an or. There's a not A in there somewhere, whereas this one doesn't have any not A's. But well, we should check it out. How do you do that? We'll make a truth table. I think today I'm probably never going to need the calculator, so we'll be using the side window here for making truth tables, kind of a lot of them. So for the moment, let me just bring this over here where we can see it better. Right, so I want to make a truth table for, no, I've moved it just a little too far so I can't see the thing. How about right there? Does that work? All right, it's a truth table that's going to have two input variables, two predicate variables in it. And I'm going to have columns for both A or B and the other thing there. So here's the column for A or B. That one's easy. The other column is going to be for A or not A and B. So it's A first, poured with parentheses around not A and B. Just let me double check. I think that's a good practice, by the way. Double check when you've copied something a little complicated. Yeah, that's right. Okay, so here's our truth table laid out. Let's fill out the usual pattern of true and false on the A and B variables. Is that what we normally do, right? Alternating true, false in the rightmost column, and then groups of two, again, in alternation in the left column. All right, so A or B. Recall that when we're doing an or sentence, we just look for the row where it's false, right? Because it'll be false in one position. And A and B are unadorned here. They're just, they're literally the A and the B. So we're looking for false and false, a false on each side of that thing. That'll get us false. And everywhere else it will be true. I'm going to lightly write in the values of not A and B in here. So I hope this will be a good color to use. Not A and B, well, that's an and sentence. And sentences are true in one row, right? So what row is not A and B going to be true in? We need B to be true, so it's either that one or this one. And we need A to be false in order that not A becomes true. So that's right here, false, true. That's where this and sentence is true. So it'll be false in the other locations. Now that I think is sort of scrap work or something. I feel like I should scribble it out or erase it or something after we're done. But I'm being honest with you, I did do that scrap work, so let's leave it there. Underneath this, or in this column, though, what I really want is A's value ORed with these things. And that is going to get us, well, when A is true, it'll be true. So when it's true in the top ones. When this thing's true, it'll be true. So it's true in row 3. Only in this bottom row do we have false in both of the inputs to it. So we get a false there. And you notice that these two things, these two columns, do have the identical pattern. 3 T's, then an F in both of them. So that's an equivalence. Maybe a little surprising, but there's the evidence for it. We worked out every possibility, and they were right, or they agreed with one another in every possibility. Put this back out of the way for a second, see what the slides have to say. Oh yeah, good point. You can stop as soon as you find a place where they don't match, right? So if you do encounter a place where they disagree, there's no sense completing the rest of the table. Just circle the disagreement and say they're inequivalent. The proof that, or the argument that says they are equivalent needs to go all the way, though. You have to go completely through the table and finish it fully before you can say they're equivalent. So while that is a pretty good and straightforward way to show that two things are equivalent, and it's valid, right? It's actually a technique of proof that's called an exhaustive proof, or a proof by exhaustion. You literally just check the thing that you're trying to say is the case in every possibility. But what's the problem with it? Well, it gets old after a while. It doesn't take very long for you to get sick of filling out truth tables. It's something that could be automated, so maybe you can find some software that will fill out truth tables for you. But there's a kind of a nicer, higher level way of approaching this topic, showing that things are equivalent. So in the next group of slides, what we're going to do is sort of develop a way of doing algebra. That is, you have certain rules. Remember, in ordinary algebra, it's okay to add the same thing to both sides of an equation. It's okay to subtract the same thing or multiply both sides, as long as you don't multiply by 0. There's a couple of algebraic moves that you can do. And one way to show that an equation is true is to slowly transform the left side of it into the right side of it. That's sort of the approach we're going to do here. We're going to come up with some algebraic moves that are legal, and we will use them. We're going to have to strategize. So this is a little bit higher order thinking, but the strategy is aimed at transforming the left side of the equation into the right, or possibly vice versa. I'll say something about that. It's often the case that our minds are better at moving in the direction of making things simpler. It just feels right. So I often put the more complicated thing on the left, the simpler thing on the right, and so I will be going from left to right. But it's not universal. You can choose which way you want to do it. But before we go on to do that, we should actually do a few more truth tables, because it's good practice, and likely there'll be some quiz questions on things like this. So I've got a couple of examples to do via truth tables. Here's the first one. Show that A ANDed with A or B is equivalent to A and B ORed with A. That's a little bit hairy. Let me just go ahead and set up our truth table initial stuff as usual. So of A and B, columns for the two of those, with the usual patterns of trues and falses. Let's work out, or let's copy in what are the headings for the two columns that we're going to want in here for the two statements we've got. A, this one is ANDed with A or B, the A or B in parens. And the other one is A and B ORed with A. I was kind of double checking those as I wrote them down, so I'm pretty sure I copied them right. we'll use the same trick of kind of penciling in the truth values under the parts that are in parentheses to make our lives just a little bit easier. A or B, an or sentence, right? So it's false just where the two inputs are false, which happens down there, and then it's going to be true every other place. You might as well pencil in the A and B. That's true just in the top position and false everywhere else. Yeah. So now let's get the other pen and write in what the real results should be for these rows or these columns. In this one, we want A ANDed with that. Well, that's going to only be true if both sides are true. So I'm going to try to point at it. Here it's a true and a true. There it's a true and a true. Then a false and a true, and then a false and a false. So, but you got to have both of them true to make that work. So it's true, true, false, false. This other guy, it's the or of what we did here, A and B, together with A. So that's when either one of them is true. So again, let me try to point at it. True and true, great, it'll be true. True and false, still true. False and false, false, and false and false. Okay. How did that go? It was true, true, false, false. Do you see that they're equivalent? The same pattern, TT, FF in both of them. Isn't that fun? All right. Last one, I think. Here's the equivalence we're trying to prove. A and B or not A is equivalent to, it's the same thing as A and B. I should probably have pre-printed a bunch of these truth table setups, and then it would be a little bit less work to do. But it doesn't take that long. Once you get into it a little bit, you do these a million times, and you get pretty fast. The actual expressions are a little tougher. I'm going to put in A and B first right here, because that one, I know what it looks like. Right? It's got a T upstairs in the first row, and then F's everywhere else. The other thing, though, I'll have to work out what its pattern is. That was A ANDed with B or not A. Great. So another place for the penciling in moment, I'm going to figure out what B or not A is about. Okay. This is good practice, though, right? It's a disjunction, an or. So, or sentences, that's the ones that are true most of the time and false in one position. Where is B or not A going to be false? It's where B is false and A is true. It's right there. It could have been B false, but this false would, that's the usual place where the or sentence is false. So yeah, this makes sense that it would be the other one. Yeah, see that in row 2, B is false, A is true, so not A is false. False or false gets us false out here. And everybody else is true. Now we're almost done. We want to AND that with A. A is true and basically in the top half of the table. So it's definitely going to be false down here. An AND sentence needs to have both things on either side of it be true. And it's only true in the top row, where this one is also true, T and T, but here it's T and F in row 2, so that's false. And like before, we see the exact same pattern. True, then 3 falses in both of those, so equivalent. Okay, so I think that was pretty good practice. Oh gosh, there's one more. All right. No, this one's going to be tough because it's going to take 3 columns for us probably to do it. So I'm going to move this thing to there. You can see it a little better. Okay, so I don't know if I need to have a third column for this. I was thinking I would put down A implies B and then write down its negation. But we did enough of A implies B before that you're probably real familiar with what A implies B looks like. It's got the vacuous truth downstairs. It's got the true in column 1, or row 1, and then it's false just here in row 2. So how is the negation of that going to look? Just switch all the T's to F's and all the F's to T's. There's only the one F, so it'll be T here, and it'll be F here, here, and here. That wasn't so bad. We could figure that out pretty quickly. What is the other sentence that's underneath of my writing area? A and not B. Let me just copy that in. A ended with not B. I think we're going to be done real quick here, aren't we? Because that's an and. It's true in one position. Where is that one position? Row 2, right? It's row 2 where A is true and B is false. So not B ends up being true. And yeah, you get true here. So what do we get out of these things? Those 2 columns are identical. False, true, false, false in both of them. They're equivalent. It's messing with my retentiveness that this line is longer than the rest of them. That one should have stopped there. I can't help it now. There's no way to erase this green marker. Okay, I think that's the end of these examples I wanted to run. But, there's a couple more available to you in the homework for this section. I definitely recommend that you do that enough that you feel facile with it, that you can quickly do a truth table to determine that something's true. Right, so now that we've learned how to use a truth table to show that 2 things are equivalent, we're going to learn how to move on beyond that and show equivalence with sort of algebraic means. Well, we're going to develop some basic rules of algebra. And those rules are actually known as the basic logical equivalences, I'd say. We'll use them in the following way. Like I said before, I'll usually go from the more complicated side of an equivalence to the less complicated, but it could go the other way. Anyway, I'll start with one side or the other of the thing, and then I'll try to transform it into the opposite side in a sequence of steps that are approved, right? These are the things that we are going to look at and can't convince ourselves these are legitimate moves. They're not going to change the truth values of anything. So the basic equivalences are in table 2.2 on page 83 in GIAM. I have put them onto a single page handout, so that's there should be a link in the video description. I also have them on screen right here, so let me pull that up. Here's the handout. Let's see. I'm going to move it so that I can see it underneath of our slides, and I can pull it back up quickly. All right, so we're going to go through these laws pretty much one at a time, take a few seconds at least on each of them. Okay, but it's not working. I didn't do that well, did I? The first law is the commutative law. Notice how this table is organized. There's a conjunctive version for each law. There's a disjunctive version. And I usually try to give you something that's analogous in ordinary algebra, if such a thing exists. So the commutative law, I think you've run into before, it just says you can switch the order around. A and B is the same as B and A. A or B is the same as B or A. 2 plus 3 is the same as 3 plus 2. You can switch order around. You're in a point right now in your math career where you're about to start encountering things where that is not the case anymore. That is, you cannot just change order around like that. Um, is it worth our time for me to show you an example? Well, if you've seen matrices before, you probably have already seen this, that a matrix A times a matrix B, it's not the same if you do B times A as A times B. Um, Physical motions in space, there's some operations you can do that just don't commute. Um, you often, after a course like this, you'll take a course in abstract algebra, and it's rare that things commute in abstract algebra. That's a special situation. Literally, there are people who study that scenario. They're called commutative algebraists, but most operations are non-commutative when you get into higher order things. Anyway, that seems like a fairly trivial thing. Both and or satisfy the commutative property. So I like to point this out. You can change the physical order on the page. A and B appear in A to the left, B to the right. You can just switch them. B then A. Also, A and or both satisfy the associative property. Now that's a little more interesting. The associative property says basically parentheses can go anywhere you want. So if you have three things in a row, you can parenthesize the ones on the right, and then that means do the and of B and C first, and then and it with A. Or you can parenthesize the ones on the left. Do A and B first, and then and that result with C. Same thing is true of or. You can parenthesize on the right side, parenthesize on the left side, and that works for addition. It also works for multiplication, right? There's a lot of algebraic analogs of the associative law. Associative laws are so powerful and so necessary that even in most abstract algebra, you have associativity. When you lose associativity, things get very, very hard. So if you know people who tell you that they're a non-associative algebraist, respect them. That's tough stuff. Okay, so you can reparenthesize any way you want. That's actually called the generalized associative property. If you've got five things in a row, you can put the parens in however you please. In fact, we often drop the parentheses entirely, provided all their operations are the same, because, well, this is much like the multi-input AND gates we used when we looked at recognizers in 2.1, I think that was. Here's a good thing to note. Commutativity is about spatial order, and associativity is about temporal order. That is, commutativity is how the things appear from left to right on the page in front of you. Associativity is the parentheses. The parentheses tell you when to do something, that you should do what's inside the parentheses first and then do the next thing. So spatial order, temporal order. They're really both about changing orders, though. Linguistics. Why did I put that bullet in? Because some things are just patently clear from the way language works, from the way we understand language. If I say, hey, it's cold and rainy outside, is it any different than if I say, oh, it's rainy and cold outside? No, those are the same. So we hardly ever pronounce things well enough to get across associative property things in language. But as a math person, you should try to think about that a little bit. When you're speaking something that's parenthesized, you need your voice to let the listener know how it's parenthesized. You can use extra words. For instance, let's go back to one of these. I could say A and the quantity B and C. That's we always say the quantity when we're talking about numerical things. I'm not sure if I'd want to say that when it's a logical thing, but that would still make it clear how you meant it parenthesized. The other way you do it is with a slight pause. A and B or C, or sorry, B and C in this case. So that's what I meant by the linguistics things, that language can sometimes make these things apparent because, if I put the pause in a different place, does that change the meaning of the thing? If it's like A and B and C, that doesn't really sound different from A and B and C. Maybe it does, but they do have the same meaning. Which, if you really feel like it, we could do it on a truth table. We could pull one of these. Oh no, that's frozen. Excuse me, I had to do a little hacking to straighten out the video frozen. So where were we? We were talking about using language. I think we covered that, but there's one other place where you can kind of visualize the differences between, not the differences, the similarity between the two sides in some of these laws, the associative and the commutative law. And for that, I'm sorry, I need a different thing. Here it is. So there are logic diagrams. This is the one I want to show at first, that again make it pretty obvious that an equivalence is true. This is illustrating the commutative law. We've got an OR gate here, right? And you need to remember what's inside of an OR gate that makes it produce the OR output. Essentially, there are two transistors that are wired in parallel inside of here. So if A is energized, current flows through the one transistor and goes to the output. If B is energized, current flows through the other transistor and goes to the output. If they're both on, we get sort of extra current. It will actually raise the voltage slightly on that line, but these circuits are designed with a little bit of fault tolerance so that anywhere between like 4 and 6 volts is counted as on. So what difference does it make whether it's the top one that's energized when we do A or B, or I guess it would be the bottom one that's energized if we do B or A? None. The fact that those transistors are wired in parallel makes it quite immaterial which one is the one that's carrying the current. So the commutative law is there for that. This is the commutative law for an AND. The only difference now is that the things are in series. But again, they both have to be energized in order for the energy or the voltage to appear on the output line. And so what difference does it make which one comes first and which one comes second? So long as the two of them need to be on before we get output, you've got a symmetry there. Okay, so let's see what our next slide has to say. Oh yeah, the next line of this table we're looking at is the distributive laws. Whoa, I didn't mean to highlight all that. Wow, it's hard to highlight within a table. So distributive laws, this third row of our table. These are what you're used to. Look at the algebraic analog. 2 times 3 plus 4 is 2 times 3 plus 2 times 4. So in ordinary algebra, when does an operation distribute over another operation? You've got basically these three operations: addition, multiplication, and exponentiation. So when do they distribute? I put them all down here. This is multiplication over addition. A times B plus C, that'll be AB plus AC. That's true. That's a valid rule. Here's exponents over multiplication. A product inside the parentheses raised to the nth power. Oh, I typoed it though. This should say a times right there. A to the n times B to the n. I'm not going to bother fixing that, but maybe in the version of the slides I put up on YouTube, we'll fix that. It looks like the exponent just comes off from the outside of the parentheses and hits in here in two different places. Once on A and once on B. But this is not true. Well, I mean, it is true because I put a not on the equal sign, but the idea that A plus B to the n is A to the n plus B to the n is false. And actually, there are three other distributive laws that are false here that we would never think to try. Would you distribute adding over multiplying? That would just feel too weird. I think you're trained out of that. But this one, for some reason, looks natural to us. It's not true, as you can tell by sticking some small numbers in. Like, suppose A was 2, B was 3, and let's make C N 3 again. Then 2 plus 3 is 5, and 5 to the third power is 125. Right? But 2 to the third is 8, and 3 to the third is 27. Do 8 and 27 add up to 125? All right, so there's actually a name for this. People often in first semester calculus will make this kind of mistake. You know, x plus y squared is x squared plus y squared. It just feels like it ought to be how it works, but it's not. Really, you need to FOIL rule x plus y times x plus y, and you get, there's the missing term is twice xy. They actually call that the freshman fallacy. So it's sexist and derogatory towards first-year students, but there it is. The thing to notice is, some of these operations are repeated versions of the other things. Multiplication is repeated addition. Exponents are repeated multiplication. So the repeated version distributes over the unrepeated version. That is, multiplying distributes over adding, and powers distribute over products. But you can't jump a generation in that hierarchy. So how does this work in logic? Conjunction distributes over disjunction. That is, and distributes over or. But the thing is, and or are sort of unrelated to one another. It's almost weird that they distribute the way they do. They're not. One's not a repeated version of the other. Sorry. So actually, both distribute over the other. Conjunction distributes over disjunction. Disjunction distributes over conjunction. There have to be two different things, though, to talk about a distribution. So if you look at this equation, A and B and C, no room to do distribution. If you try to distribute that, it'll turn out to not be wrong, but it's entirely wasted effort. It results in something that you could just undo. So it won't get you anywhere. So don't think that you should distribute in that scenario. What you might want to do in that scenario is reassociate. The operations of being all the same says you can use the associative law. The fact that they don't have two different operations means don't think about distributing there. Okay, well, we've been knocking our way down this table pretty quickly because the first three things are pretty standard, I think. We know what distribution looks like. We certainly know about what associative and commutative law. De Morgan's law is something new, and it's somewhat unique to logic. Let me jump back to this. You'll notice in the table, I just said there's no algebraic analog to it. There actually is something. A student actually suggested this to me, so we'll come to that in a sec. Okay, so we're going to think about truth tables for a second. If I look at a conjunction, I know it's true in one row of a truth table, and so that says something about its negation. The negation of a conjunction is false in just one row, and it's going to be true in 3 rows, right? Well, what kind of a sentence is true in 3 rows? Right. A conjunction's negation has to be a disjunction. And you can argue similarly that the negation of a disjunction must be a conjunction. This means that something that looks like it ought to apply is not good. So if I have the negation of A and B, doesn't that look like a minus sign outside of, say, a product or a sum? And you would distribute the minus sign in just like you would distribute like multiplying by -1 in? But that's wrong. It's just not right because both of those things, well, they're true in the wrong number of places. The one on the left has three t's in it, and the one on the right has only a single t in it. It can't be right. The correct thing is known as De Morgan's law, and in words, you not only distribute, oops, I just spelled distribute wrong. Distribute. Anyway, you not only distribute the negation sign, you also change the operator. So let's see De Morgan's law and look at it. Here's a not out in front of A and B, and it's equivalent to not A ORed with not B. The disjunctive version is when you have a not out front of A or B. When you distribute it in, you get not A and not B, but you turn the or into an and. So what is this algebraic analog that it's not quite algebra, but remember doing things like this. If you have 2 is less than 3 and you need for some reason to multiply by both sides by a -1, well, when you do that, you get -2 and -3. But remember that you have to switch the direction of the inequality when you do that. That's how that works. So it's an instance of sort of distributing the minus sign and then also changing the type of the operator. So it's somewhat like what De Morgan's law does. I'm not sure if there's any theoretical underpinning to why that's true. I just wanted to give you something that give you a sense of an analogy there. De Morgan was a pretty interesting character. I believe he was the first one to formalize this idea too. I don't have a lot to say about this. If you negate a sentence, it turns all of the T's in a truth table to F's and all the F's to T's. And if you do that again, you're back where you started, right? Double negatives are the same thing as positives. There's a slightly corny joke about this where like a linguistics professor is talking to his class about how some cultures use the double negative to emphasize negativity, makes it even stronger. Other cultures say double negative is positive. Some cultures use an affirmative followed by a negative to emphasize the thing, but no culture is known that does 2 affirmatives to indicate dissent or negation. And a voice from the back of the room says, "Yeah, right." I love that joke, but maybe I shouldn't have told it. Whoops. Anyway, that's all I have to say about double negations. If you have a not of a not, it's the original thing. There's a group of, let me return to our table, a group of several things coming up here. We just did De Morgan's law, and then, sorry, the way that highlight stinks, double negation there. The next 3 things, you'll notice if you look in the interior of the table, they involve some new symbols we haven't seen before, T and C. So let's talk about them. T is what we use for a statement that you know is true. It's always true. In any situation, it's true. It's just truth embodied, right? You write C for the similar thing that's always false. The words for those kinds of statements are tautologies and contradictions. So T for tautology, not T for true. C for contradiction. This is different from the capital T and the F, the phi that I've been using, because those are just truth values. This is a statement that has that truth value. So the 3 sentences coming up, one is called complementarity. Might as well look at it on the handout. Complementarity says here, A ANDed with not A is equivalent to C. Think about that. If you have an and statement that's surrounded by a logical sentence and the negation of that logical sentence, are you ever going to get true on both sides? No, if it's A and the negation of A, then what's on both sides of that is automatically opposite to one another. If one side's true, the other's false, vice versa. So how can that and ever turn itself to a true statement? It can't. It'll always be false. So you get a contradiction. A similar thing happens if you have an or sentence that's got a statement and its negation on either side. One or the other of those 2 things is true. So you always get true out of it, no matter what. Now, I don't know about maybe this is similar. 2 plus minus 2 gives me 0. It's kind of like what A and not A gives me the contradiction means. I'm not sure how good that analogy is. The next line of those, let's just bump the slides while we're going. That's the identity law. That's the next thing we see. Look at the analog first. It's 7 plus 0 equals 7. Yeah, I suspect at some point you've heard people call this 0 the additive identity or an identity. 1 is the identity for multiplication. 0 is the identity for addition. Well, so what does an identity mean? It literally is something that you can do the operation with that thing and leave the other guy unchanged. When I add nothing to 0, I just get 7. Funny way to misspeak. When I add 0 to 7, I just get 7. If I have a statement and I AND it with a tautology, it does nothing. It just gets me that statement back again. It's a little bit like if you think about the circuit diagram. I have statement A coming in on a line, going into an OR gate, and the output is that, but what's on the other branch of the OR gate is just tied to the battery. So, juice is just flowing to this side. As soon as A comes on, this comes on. If A goes off, this goes off. See how the output is going to do exactly whatever A does? That's the logic diagram way to think about the identity law. That's the identity law for conjunction. So T is the conjunctive identity. What's the disjunctive identity? I can make a similar diagram, but it's the same idea. If you OR a sentence with something that's false, that's like saying you're disconnecting one leg of the OR gate, and the other leg entirely determines it. You've got 0 volts on the bottom leg. I don't care. Whenever A comes on, the OR gate is going to energize, and so the output will be on. Whenever A is off, now we've got 2 offs on the input leg, so then it'll be off. So it just does the exact same thing as A does. Great. Our next law is called domination. We only see domination in one place in ordinary algebra, multiplying by 0. If you multiply by 0, you get 0. That is, where adding 0 left the input unchanged, multiplying by 0 crushes it, dominates it, it makes it 0. And there are versions of domination. There are 2 versions of domination in logic. For ands, anding with a contradiction just produces a contradiction. Because one side of the and is definitely false, and so the and never has a chance to be true. It's always false. On the other hand, ORing with something that's tautological, a true sentence, that's just getting to get you something that's tautological. Because as long as one side of the OR operator has a T on it, has a true thing on it, it's going to give an output of true. So I tend to think of those 3 as a group of things because they all involve the C and the T things. And that's what we've done here. The next group of things, they don't really group together for any good reason, just because we're coming to the end of the table and I'm throwing them all together. The first one is called idempotence. Idempotence literally means same power or equal to your power. And I want to ask you for a second what it would mean in logic to do something like a squared. In ordinary algebra, squaring means multiply 2 times in this case. A squared equals A times A. But if we're in logic, that doesn't make sense. So really, I could probably define 2 different kinds of squaring. Maybe I do a 2 on the left, but still in the subscript notation, I'd call that the meaning of A and A. And perhaps 2 subscripts on the right would be A or A. But these things are unnecessary because of the idempotence property. A and A, that doesn't really do anything new. If you AND a statement with itself, well, when A is true, you'll get true, and when A is false, you'll get false. In other words, you get the same exact values as A. Similar thing happens with or. If you or a sentence with itself, you get itself. So let's look at that on the table. That's this next to last row, idempotence. A and A is equivalent to A. A or A is equivalent to A. 1 times 1 is equal to 1. I guess that's an analog. I'm not sure if that makes much sense. But last thing on here is absorption. And frankly, absorption only exists because we found that were some things that were equivalent that we could not show were equivalent just using all the other things. Surprise. There's no algebraic analog to this rule. It seems weird at first. Wrapping your head around absorption is a great idea, but it's hard to do. So just sort of memorize it at first, and you will come to appreciate its power. What it says is that this conjunction with a disjunction, A ANDed with A or B, doesn't actually depend on B. It's just equal to A, or it's equivalent to A. And if you switch the ors with the ands, so you get the other version of it, that's also just equivalent to A. The best way to see this is to do a truth table, which we actually did earlier. I had a truth table for the 2 of these things. I believe the second one was the order swapped around, but that's just the commutative law. And they're both equivalent to A. I wish I had saved the piece of paper because I think I could show it to you now, but yeah, it's not here. Being sloppy in my little studio here and just threw it on the floor, I think. I was right about that, and so I found it. Remember we had A and A or B, and we got TTFF, but notice what A's values are, TTFF. And A and B ORed with A. Like I said, that's the thing in this second position, but just with a commutation of the part in parentheses with the other guy. It also has the pattern TTFF. So they're both equal to A. That makes them equal to one another as well. Finally, on the slides, there's one other thing, which is, oh, I forgot to advance the slides here. Yeah, there's really no such thing as exponentiation in the algebra of logic. I said that to you because as soon as you get to the square, you're back to the first power. So try to the cube, back to the first power again. We did absorption. I call absorption a weapon of last resort. That's probably not true. There are occasions when you go, oh, this is perfect. I just see absorption staring at me, and I can simplify something a lot in one fell swoop. But the one thing that's not on this list is the equivalence of a conditional and the related disjunction. Because I don't think of that as one of the basic equivalences, but it is something we know now, and so you can use it. A implies B can be replaced with not A or B if you need to. And it's not a bad way to see certain things. Let me give you a quick example of an equivalence using that. If I wanted to figure out what's the negation of A implies B, well, that's equivalent to, I don't know how to negate A implies B. Actually, we do know how to do that because we proved it with a truth table, but let's pretend we hadn't seen that. But I do know that A implies B can be replaced with this disjunction, not A or B, right? And then this is a not outside of something with parentheses in it, so I can apply De Morgan's rule, which says bring the not onto the inside, change the operation, and bring the not into the inside on both bits. Maybe I need parens here. Well, that's the double not rule, so that's A. And the other thing is unchanged, A and not B, which is what we figured out was the proper way to negate a conditional. Now, if you're really doing this and trying to prove it to somebody, you're supposed to sort of give an explanation for each step that you take. But Well, that's what's coming in our next chapter, so I think I'll leave that where it is for now. Finally, do we have time? I think we'll be all right. The Island of Knights and Knaves. I wanted to tell you a little bit about Raymond Smullyan, who is the person who came up with the Island of Knights and Knaves. No longer need these. I preloaded the Wikipedia page for Raymond Smullyan. This is him. Well, I'm currently filming in 2020. That's him in 2019. If you look on the Max Hooter History of Math archive, they have some pictures of him as a younger man. Had a really impressive mane of hair for me, particularly. That's probably the coolest thing about him. No, he was brilliant. He was a great popularizer of mathematics, and particularly he came up with a lot of really cool little logic puzzles. One of the most famous of his logic puzzles were the ones called Knights and Knave puzzles. So let me tell you the origin story. He didn't invent this, but he took it and generalized, made it into his own. So the origin story is about a guy who arrives in a chamber. I think it's probably supernatural. Like, so the devil puts him in this chamber, and in the chamber there's an angel and a demon, but you can't tell one from the other. You don't know who is who. The angel will be truthful to you, and the demon is going to lie to you. And here's the deal: there's two routes out of this chamber. One of them will lead you to heaven, and the other back to hell. So you're tasked with figuring out how to get out of this situation, ideally by going to heaven, by only asking a single question. And it turns out you can do that if you're clever. What you do is you ask either one of them what the other guy would say to do. The angel knows that the demon will lie, so he truthfully will tell you that the demon will tell you the wrong place to go. And the demon knows the angel will tell the truth, so he lies about that, and they both end up telling you that the place to go is to go to hell, and so you just take the other one and you end up in the right spot. So Smullyan took that story and created Knights and Knaves, and I like the alliteration of the K's and that the KNs and that K's with silent K's with N's. Famously, oh God, I have to admit something really kind of embarrassing. There's this Monty Python movie called the Search for the Holy Grail or something like that. And in it, there's these very annoying French knights who keep calling the other guys Kniggetts. And I had no idea what they were doing when they called these other guys Kniggetts. They were pronouncing it phonetically. Just didn't notice when I was 14 anyway. Well, okay, so knights always speak honestly. And knaves, honestly means they make true statements. Knaves always speak falsely. They always tell you a lie. They always tell you a false statement. Usually in these things, you don't know who's a knight and who's a knave, and that's actually what your puzzle is. You'll get statements from a couple of people, and you're supposed to figure out from that who is the knight and who's the knave. There could often be more than two or three. So in 2.1 in the homework, there's this puzzle about Locke and Demosthenes. I think Locke is like a British philosopher, and Demosthenes is a Greek philosopher. I'm not sure why these names were chosen. But anyway, Locke says Demosthenes is a knave, and Demosthenes says Locke and I are knights. And how do you sort that out? Well, often you can sort these things out by examining all the possibilities. There's two possibilities: either the person's a knave or a knight. So you examine the consequences of both possibilities for one of the people and see what happens to that. And if it doesn't work out for that one, you might try the other one. So let's focus on Locke first. Locke says Demosthenes is a knave. That's what he's saying. But the possibilities are he's a knight himself or he's a knave himself. If he's a knight, then what he says is truthful, right? And that means Demosthenes is a knave. Now, if that's the case, do you see that Demosthenes' statement that Locke and I are both knights is a lie? Perfect. That's what a knave is supposed to do. So that is, we haven't found anything inconsistent about the assumption that Locke is a knight. What if he's a knave? If he's a knave, this is a lie, right? So, in fact, Demosthenes is a knight, and that means this statement, Locke and I are knights, is true. But we were just supposing that Locke is a knave. So how can this be true? So the one supposition that Locke is a knight, Locke is a truth teller, doesn't cause us any issues. The other one leads to something contradictory. So I might say that Locke is a knight from that, since there's only the two options. And then he actually is telling us that the other guy's a knave. So we've got that Locke's a knight, Demosthenes is a knave. You could also focus on Demosthenes, and I think probably this is actually quicker, because look at what he says. Demosthenes says, Locke and I are knights. Could he be truthful? If he was truthful, then they're both knights, and then Locke says this, Demosthenes is a knave. If they're both knights and he's saying the other guy's a knave, then he's lying, and that means, this couldn't be truthful. So this has to be a lie. This has to be a false statement, which makes Demosthenes a knave, and then apparently Locke knew that, and he was truthful about it, so we get Locke as a knight. All right, that's the end of our slides for today. That was a jam-packed lecture. I thank you for hanging on to the end. If you did, you're not hearing my voice unless you did, so I guess not. That's 2.3. We'll be doing 2.4 in the next one. Have a great rest of your day.